All right, so actually what we're going to do now is talk about section 2.2, which is more or less a continuation of what we were talking about in section 2.1 with linear combinations of vectors. All right, so let's actually start off with an example of the type of question that we're going to consider. Um, Example 1. If possible, we want to express this vector in R2 as a linear combination of these guys. All right, so remember what a linear combination means. Can we find, so does there exist an x1 and an x2 in R? So we want to find scalars x1 and x2 such that, backwards little epsilon is such that, um, x1 times this vector plus x2 times that vector is equal to this vector, right? So we set up an equation, a vector equation in this sense, whose solution would be the scalars that would work to make this guy represented as a scalar multiple, a linear combination rather, of those vectors. So, but if you look at that, trying to determine if such an x1 and x2 exist is equivalent to solving a system of two equations, right? So this is the same. If you wrote this in system form, you'd multiply through this vector by x1, this one by x2, add corresponding entries in both those guys, and then set those entries equal to the corresponding one on the right side. And so what you get is x1 plus x2 is 5. If you read through the first guys, multiply those, and that's it. That's sum equal to 5. Same way here, x1 times 0 is 0, 2x2 is equal to 4, right? So asking whether or not this vector is a linear combination of those two vectors is equivalent to asking if this system has a solution. And we clearly see it does. Remember, this is in a kind of a staircase sort of form. We know that's going to have a solution. We'll start from the bottom up. X2 is equal to 4 over 2, which is 2. And you plug that x2 back in the first equation to get x1 is equal to 3. And so therefore, the vector 5, 4 that we began with is indeed a linear combination of u1 and u2. Namely, you multiply x1 times u1, oops, and multiply x2, which is 2 times u2. Okay, so the answer this time is yeah, you can, and that's equal to, this is a 1, equal to that linear combination. Okay, so, but what if, is there anything special about that vector 5, 4, right? Could we have replaced it by negative 117 pi, right? Something like that. Can you always express any vector in R2 as a linear combination of those guys, right? So that's a more general question, and it motivates the following definition. If I take m vectors in Rn, right? So in this case, I took two vectors in R2. The m and the n at the moment don't have to be the same, right? N could be 3 and m could be 17, or vice versa, right? But you take those m vectors, the span of those vectors, and we denote that by using that notation, is the set of all possible linear combinations of those vectors. So every vector you can construct by a linear combination of these guys is in what we call the span, right? And these x1 through xm are just numbers. If the span is equal to Rn, so in other words, every vector in Rn can be written as a linear combination of those guys, then what we say is that the vectors span Rn. That's just terminology. All right, so let's go on. Let's actually look at a lot of examples, right? So let's look at, let me make this smaller. All right, so let's determine the span of these vectors. So what does that mean? Let me write the definition here, just kind of making it more operational, if you will. We know that a vector AB belongs to the span of m vectors, right? If Let's actually just take it u1, u2 just for simplicity. I can do this in general, but I'm just going to look at what it looks like for R2. Right? So we'll say a vector is in the span of those two vectors if there exist x1 and x2 in R. So you can find scalars x1 and x2, right? Such that the ordered pair x1, x2 is a solution of the system that you get by considering this vector equation. All right. So in this case here, right, what we want to do is multiply x1 times 1, 0, and x2 times u2, okay, or 1, 2. And what we're going to do is we're going to set that equal to AB, right? AB is kind of a fixed but arbitrary vector. And what we're going to ask is, for what vectors on this side does this system have a solution? Okay. If there are absolutely no restrictions on the A and the B in terms of whether or not this system has a solution, in other words, if the system has a solution for any choice of AB, then the span is all of R2. All right, so let's consider this in matrix form, right? So we already saw how to write this in vector form. Multiply the x1 through, the x2 through, add, and then set the corresponding components equal. But let's write this as an augmented matrix. It's 1, 1 bar A, 0, 2 bar B, right? So we can write any system as an augmented matrix, all right? And remember, the solution of this system is the pair of scalars you need to make that linear combination, right? Just keep in mind what the solution represents in this case. Okay, so this, notice it's already in what we call echelon form, right? Any 0 rows are at the bottom. There are no 0 rows. Every row has more zeros in front than the one previous. That's all we need, right? So this is always solvable. In fact, what we get is that 2x2 is equal to b. So your solution for x2 is b over 2. And if I plug this in for x2, I have x1 plus, that would have been x2, or b over 2 is a. And so that x1 is a minus b over 2. Okay. And so in this case, the vector AB that I started with, this is that arbitrary vector that I started with here, is in fact a linear combination of these guys, right? It's x1, it's a minus b over 2 times that first vector u1, right? This was u1, plus b over 2 times u2, right? And that's for all a and b I choose in R. It didn't matter what the a and b were, that worked for any such vector. And so in this case, the span of u1 and u2, the set of vectors in R2 that can be written as linear combinations of u1, u2 is all of R2. Okay, so those vectors in fact span R2. Not bad, right? All right, let's do the same thing here, right? We want to find the span of those vectors. So you want to multiply each of the vectors times an x1 or x2, a scalar, and I'm going to set that equal to a fixed but arbitrary vector AB. And again, we ask the same question. Are there any restrictions on A and B so that that system has a solution? All right. Well, let's write it as an augmented matrix. This will be 2, 6, A, 1, 3, B. Remember, if we wrote this as a system, we would pluck off the coefficients. That's where I'm getting this. The right side is A, B. All right. Notice that's not an echelon form, right? So I want to put it into echelon form, which means what I'm going to do here, I want this guy to have a 0 where the 1 is, right? And so I'm going to multiply the first row by minus 1/2, add it to the second row, and replace the second row by that. right? If I do that, the first row doesn't change. But this time, if I do that, if I multiply by negative 1/2 and add, that'll be a negative 1 plus 1, which is a 0. A negative half of 6 is negative 3, plus 3 is 0. And negative half of a is negative a over 2 plus b, that's b minus a over 2. All right. So now this is a little bit different than it was before. We don't have a row of zeros, but we do have this, which is kind of a struggle, right? What that's saying, if you were to translate this back into a system, this says that in order for this system to have a solution, this, in order for it to be a true statement, this has to hold. Well, that's a condition, right? If this doesn't hold, right? So if b is anything but a over 2, then if I plug in an ordered pair with such a b, this system will not have a solution. It'll lead to a false statement, right? So this has a solution if and only if that holds, namely b is a over 2, right? And so for such b then, right? So we know the vectors for which this that will be able to be written as a linear combination of those guys. They're any vectors of the form a over 2, right? So the span, remember, all the span is the set of vectors that can be written as linear combinations of the two guys that you're spanning or that you're using to span. So the vectors have to be of this form where a is a real number. But notice that that is a parametric form for a line, right? So what does this mean? If you were to rewrite that, it is x equals a and y equals a over 2, where a is a real number. But I can eliminate that a. If I want to see a picture of this in the plane easily, or an equation of this in the plane not involving that third parameter, I'm just going to plug in x for a, right? Because x is equal to a. That gives you y is equal to x over 2. And since x is equal to a and a was an r, x is an r, right? And so what that says, x over 2 is a line with slope of half and y-intercept is 0. And so here's this line, okay? So the span of these two vectors in R2 is in fact this line. It's not all of R2. You're just going to get this line in that case. Okay. Now, a little bit of insight in terms of why that's happening. Notice here that U2 is a scalar multiple of U1, right? Now, notice that U2, in fact, is equal to 3U1, right? So there is a dependence relationship between U1 and U2. We'll explore that in the next section, but just keep in mind that there is probably some connection between the vectors you're starting with that will prevent them from spanning the whole space, right? And that's kind of what's happening here. Okay, let's go on to the next example, right? We don't have to just look at vectors in R2, we can look at R3 as well, right? And so let's look at these three vectors. And we want to know, first off, if that vector is in the span of those guys, right? So what we know is same sort of thing. We're going to have x1 times, I'm going to write these as column vectors. Remember how we can go back and forth. x1 times u1 plus an x2 times u2 plus an x3 times u3. And that's equal to 6, 7, 3, right? So does there exist, or do there exist, scalars x1, x2, and x3 in R such that that has a solution? All right. Well, let's write this in as an augmented matrix. So you have 1, 1, 0. Notice the vectors that I'm trying to find linear combinations of form the columns, right, of the augmented matrix. And the right side is the vector that you're trying to determine it's in their span, right? So there's that connection. The vectors that you're computing the span of are the columns, and the right side is beyond the bar. Okay, so this is still not an echelon form. What I'm going to do, I need to put a 0 here, right? So what I'm going to do is I'm going to multiply R1 by -1, add it to R2, and replace R2 by it. Okay, so I'm not going to change either as row 1 or 3. All right, I have 1, 1, 1, 6. This guy, if I multiply this guy by -1 and add to row 2, I get a 0, a 1, a -2, and a 1. And then the last row doesn't change at the moment. All right, still not an echelon form. I need at least a 0 there. And so the next thing I'm going to do is multiply row 2 by R1, add it to row 3, and replace row 3 by it. Right? And so if I do that, again, the top row doesn't change, the second row doesn't change, but the bottom row now becomes 0, 0, 0, -1. Right? If you can see that by multiplying this by -4 and then adding to row 3. Right now, but notice the last row is another problem. Right? This gives you the statement 0 equals -1. Right? And so since this is for this given vector, if you try to solve this system, you get that row, which is false. And so what that means is that the system is inconsistent. There is no solution to the system. Okay. And so if that system is inconsistent, this means that V, the vector that we started with, does not belong to the span of those three vectors. All right. So it all boils down to solving a system and seeing if there is a solution. If you're doing it in general, if you're trying to find the span of three vectors, then you're trying to determine if there are any conditions on the components of the vectors that are in the span, if there are any sort of conditions on them. If there aren't, if the system has a solution for all choices of those components, then they'll span all of the space. All right, so let's do the same sort of thing we did for R2. Let's actually determine the span of these three vectors, right? So we want to set up, right? What does this mean? A vector, this time we have this, if it's an R3, we need three components. So a vector ABC is in the span of three vectors, right? If there exist now three scalars such that that ordered triple is a solution of this vector equation, right? You multiply each of the vectors by scalar, add them up, right? So this would be the linear combination of these vectors. And what you're asking is, can I find appropriate numbers to multiply those guys by so that when I add them up, I get the vector ABC, right? So we're going to start with that vector, right? So I'm going to multiply. Remember, I'm going to put in U1 here. This is my U1. This is my U2. That's my U3. And as I said before, since the solutions X1, X2, and X3, the columns of the augmented matrix are simply these vectors written as column vectors, right? So it's 1, 1, 0, 1, 2, 4, 1, -8, net 1, -1, -8, bar, ABC, right? So we're trying to find what conditions, and we know they're going to have to be because we just saw that there was a vector that wasn't in the span of them, right? So this is not going to have a solution for all choices of A, B, and C. There's going to be some restriction on them somewhere. We have to find what it is. All right, so the first thing I have to do is put this into echelon form. So I'm going to do the same thing I did up here, right? Same thing works to put it in echelon form. I'm going to multiply row 1 by -1 and add it to row 2. right? So notice I'm going to get the same left-hand sides here, right? First row doesn't change. The second row changes to 0, 1, -2. But now remember, I multiplied the first row by -1. There isn't a -6 there, -6 there anymore. It's now going to be -a. So I get a b minus a. And then the last row doesn't change. Okay. And finally, same thing here. I'm going to multiply row 2 by -4, add it to row 3, and plop that into row 3. Okay, and so what that gives me, top row doesn't change, second row doesn't change, but the bottom row does, right? The bottom row becomes 0, 0, 0. I multiplied this by -4 and I added it to row 3. So it's negative 4b plus 4a plus c is there. All right. And so here again, now notice, had there been a number here other than 0, I don't care what the number would have been, anything but 0, this system would have a solution for every choice of A, B, and C, right? It would have been triangular. But the fact that there are all zeros here gives you the condition, right? So this means that the only way this is going to have a solution is if this produces a true statement. And so 0 would have to be minus 4b plus 4a plus c, right? That would have to happen. So this system has a solution if and only if this condition holds. And so what that tells you is that A, B, C, that vector is in the span of these three vectors if and only if that happens. And I'll write it like this. Okay. But that determines a plane, right? Because if you look at the parametric form here, we have two. So if the vectors look like this, I'll put it over here. We have A, B, and the C, if I solve for C, is 4B minus 4A. So I have X equals A, Y equals B, and Z is equal to that guy. If you think about, and this is A and B are both in R. Okay. And so X is A, Y is B, and so Z is 4Y minus 4X. And so that's a plane that passes through the origin, right? Somehow or other. So, and you can actually plot these if you want. I'm not going to bother, but it's not going to be all of R3. It's just some portion that passes through the origin. All right. Oops. All right, let's look at another example. Oops. I have to keep remembering to shrink it down and then do this. There we go. All right, so let's do the same thing here, right? What is the span of these three vectors? So right off the bat, we're going to go through, we're going to set up the augmented matrix directly, right? So by seeing the A, B, and C for which this system has a solution, that's equivalent to determining the span of these three vectors, these column vectors. So let's go ahead and put this into echelon form, right? I want to clunk zeros there and there. And so I'm going to do these things. Instead of doing it one at a time, I'm going to do them both at the same time, right? So I'm going to add R1 plus R2, right? Because that'll give us 0 there, and replace R2 by it. And then I'm going to multiply R1 times the first row and add that to the second row. Okay, so if I do that, you can check the arithmetic here. But if I perform those operations, I get that guy, oops, and that guy. Okay. And now that's still not in echelon form. I need a 0 there. And so I'm going to multiply row 2 times -2, add it to row 3, and that put that into row 3. Oh, not by -2, pardon me, +2. Sorry about that. Just already negative down here. So multiply by row 2 by 2, and then add that to row 3. And so then what I get is top row stays the same, second row stays the same. The bottom row now becomes 0, 0, 1, -a plus 2b plus c. Okay, and so now this is a very different situation than it was in the previous problem. Notice here there's not a 0. And so this system has a solution, a unique solution, in fact, no matter what the A, B, and C are, because we say it's triangular. It's in that step case or staircase type form where there is a pivot, or I'm sorry, yeah, a pivot in each of the rows, right? There's a leading term, right? And so this has a unique solution. You can go through the actual gory detail to find it, right? This is just z equals that, then you plug this in backwards, back substitution. So use back substitution. But I don't need that. I know that there is a solution, and all I was trying to do is find the span. I don't care what the actual linear combination is. I just know that it has a solution because it's upper triangular. And that's the terminology we use for that system, right? So zeros down here, non-zero entries along the diagonal, right? Could be zeros up there if it want, but up here on the diagonal, no zeros. Upper triangular, and so the span of, and we call these vectors u1, u2, and u3, the span of those vectors is all of R3. Okay? All right. Good enough. Right, and so this is just an observation, right, that we've now made this over several examples. In particular, the only way that vectors are going to span a space is that in the end, there are no 0 rows in the echelon form of the augmented matrix, right? A 0 row, we noticed, would lead to an inconsistent system for some choices of the vector. Not necessarily, not all of them, but it could lead for, there have to be a condition imposed on the components. And the minute that happens, a vector that doesn't satisfy those conditions is not in the span. Right, so this is a key sort of result here, is that vectors will span a space if and only if there are no 0 rows in the echelon form of the augmented matrix. Okay, so let's do this. We have 4 vectors in R3, and we want to know, do they span? Right, so this time around, again, remember, the columns form, I'm sorry, these vectors form the columns of the augmented matrix. So I don't need to write the system every time, but remember where it's coming from, right? And I want to start with an ABC, right? So start with a generic vector in R3 and see if there are any conditions that have to be imposed on those coordinates to ensure the system has a solution, right? So if I put it in echelon form, I have R1 plus R2 into R2. Or so I want to put a 0 here and here at least, and then minus 2R1 plus R3 into R3. Right, so the normal sort of thing that we do. And if I do that, the top row stays the same. You can check all this. The bottom row, let's see if I add R1 to R2 plus B, and then the bottom row is 0, minus 2, minus 6, 2, and then C minus 2B. Okay, and now I want to put a 0 there to get an echelon form. And so I'm going to multiply R2 by R1. I'm sorry, R2 by 2 and add it to R3 and plug it into R3. All right, so the first 2 rows remain the same. And then down below, I have, if you were to do that, I get zeros all here. And let's see, I have a 2a plus b plus a c minus 2b. Okay, and so now notice, aha, we have zeros here, but not zeros there, right? And so here, what you have to keep in mind is that the minute that happens, of course, then you don't have we know that these vectors do not span R3. So that's the first thing, right? So the presence of this zero row here, this implies the vectors u1 through u4, the ones I start with, do not span R3. That's number one. Number two, I didn't need the right-hand side notice, right? So if I didn't want to keep track of this nonsense, if I don't care about actually finding the span, if I'm just asking whether or not the vectors span a space, then I really don't care about the conditions here. All I care about is if there's going to be all zeros on that left-hand side, because we know that if there are, then there is going to be a condition on the components, and hence the vectors can't span the whole space. And so here, I don't even need to bother with this right side if all I want to know is if the vectors span a particular space, right? So it's less keeping track of. Okay. So let's do that here. Same idea. I want to know if these vectors span all of R4. And so I'm going to put those in as my columns. And remember, if you take a vector in R4, it has 4 components. So all we have to do here, again, I'm not going to keep track of that, right? I don't need this, right? I just need to keep track of the coefficients and see if there's going to be a zero row. So to do that, let's put it in echelon form, right? So I need zeros all here. So I need 3 different arithmetic combinations, right? I'm going to multiply row 1 by 2 and add it to R2. I'm going to add R1 and R3, and I'm going to multiply R1 by -2, add it to R4, and plug it into R4, right? And so if I do that, I'm not going to bother with that right side. I'm just looking at the coefficient matrix. Okay, that's what I get. But it's not in echelon form yet, remember? Right, even though this row behaves nicely here and this one behaves nicely there, I need strictly more zeros in every successive row. And so I need to put a 0 there, and then unfortunately that means I'm going to put a 0 there, right? So you already can kind of see what's going to happen. I'm going to multiply row 2 by -1, add it to row 3, and I'm going to just interchange row 3 and row 4. Okay, and so if I do that, the matrix I get is 1 minus 3, 2, 0, 1, 4, 0, 0, 1, but then I have a row of zeros, right? So that's an echelon form because all 0 rows are at the bottom, and then each row has successively more zeros initially than the one prior. But here's the thing, there is a 0 row. And so that means that these vectors do not span that space, right? Because that would lead to a condition on these guys that we didn't keep track of. And the minute there's a condition there, that means that not every vector in R4 can be written as a linear combination of those guys. And so the span of U1 through U4, U1 through U3 rather, is not R4. It's something smaller than that. Okay, and so what this shows is if, here the dimension, so to speak, R4 was vectors of 4 components. We had 3 vectors, right? So the minute you have 3 vectors here only, you know that in order to put this into echelon form, you're going to have a 0 row. No choice, because you have to have successively more initial zeros than the row prior. The only way that's going to happen for 4 rows, and you only have 3 to go that way, is to have a 0 row, right? So certainly if you have fewer vectors than, we'll say, the dimension of Rn, which is n, then they can't span. And then finally, let's take a look at, I want to be able to look generally, oops, shrink, and now do that. Okay. So I want to write general sort of matrix or equations in matrix form, right? And so here we've been writing them in system form and we've been writing them in vector form. I want to go one step further and just in a very compact way write the left-hand side of an augmented system as a matrix times a vector, right? And so this is a special case of multiplying a vector times a matrix, right? So here I'm going to basically define what it means to have the scalar, a linear combination rather. So I'm going to basically just say this, right? So this vector here has m components attached to it, right? So I'm going to call A1 A11 through A1M, right? It has m components to it. And same way here, AM has m components. Notice I'm keeping the first subscript the same here. I'm just changing the second ones. Okay, so the m is the same. The last one is keeping track of the number of components. And so what I get is if I were to have multiplied all this out, right, what you're really going to get here is a matrix, an m by m matrix, right, times a vector, x1 through xm, right? And so what I'm defining here basically is what you, if you were to multiply each of these vectors by these scalars and then add corresponding entries across like you would add vectors, then the first component of the resulting vector that you get is obtained symbolically by multiplying corresponding components of this matrix by the components of that, right? So this would be x1 times a11 plus x2 times a21 plus all the way down to xm times am1. That would be the first component of that expansion. If you did that for every possible row, right, you'd get a vector with m components. Right, so I'm going to call this matrix A, and I'm going to call this vector X. Just a component or a very compact way of writing that. Okay, so let's do that here, right? In terms of, what does that mean in terms of writing this as a matrix equation? All I'm going to do is strip off, right, the coefficients, right? So everything, remember x1 through x4, they're all in the same order and they're lined up. So don't forget the zero entries. Those are important. So the A is just the coefficient matrix. There's no x3 here, so I put a 0. There's no x1 here, so I put a 0. 1, 4, -1. That's my vector A, or my matrix A. My vector X is x1 through x3, and now that's equal to the right side, right? So this is my A, this is my vector X, and this is my vector B. All right, so it's a nicer way, a very compact way of writing this system as an equation in which the quantities involved are either matrices or vectors. And that'll become important later as we move through, right? And trying to solve this like you would a linear equation, ax equal to b, right? If it were just an equation in one variable, we know that you would divide by a or multiply by a to the -1, right? So there's going to be some sort of connection between what you do in the one-dimensional setting and what you do in the matrix setting, right? But we'll get there later on. Okay, so try your hand at practicing all with spans, and if vectors are in spans and finding spans of vectors, blah, blah, blah. Go ahead and work away on homework 2.2, and then the next section will extend that one step further and talk about that condition on the vectors from the very beginning that would ensure they do not span or they do span a space. Okay, see you next time.